Welcome to the third part of our O-Level Physics series. Today, we're going to clear up a massive misconception, something we all get wrong in everyday conversation, the difference between mass and weight. Now, they might sound like the same thing, but in the world of physics, oh, they are completely different beasts. So think about it. When you step on the bathroom scale in the morning, what is that number really telling you? Is it measuring the amount of stuff you're made of, or is it measuring the force of the Earth pulling you down? By the end of this little explainer, you are going to know the answer for sure.
So to figure this all out, let's start with the first piece of the puzzle. Let's talk about mass.
At its very core, mass is just a way of measuring how much matter, how much literal stuff, is packed into something. It doesn't matter if you're talking about a tiny atom, a person, or an entire star. If it's a physical thing, it's got mass.
Now, mass has a few really important characteristics you gotta know. First, it's a scalar. That's just a fancy way of saying it's a number. That's it. No direction involved. We measure it in kilograms, or kg. Mass is also a measure of inertia. It's the reason it's so much harder to stop a moving truck than a moving bicycle. But listen, here is the absolute most important thing to remember. Your mass is constant. It never ever changes. Whether you're standing on Earth, bouncing on the moon, or floating in deep space, the amount of you is always the same.
Okay, so that's mass. Simple enough, right? The stuff. Now let's flip the coin and look at weight. If mass is the stuff, then weight is what gravity does to that stuff.
So you see, this is the big difference. Weight isn't actually a part of you. It's a force that's acting on you. Specifically, it's the force of gravity from a huge object, like our planet Earth, pulling on every bit of your mass.
So how does weight compare to mass? Well, for starters, it's a vector. That means it has both a size and a direction, which is always pulling toward the center of the planet or moon you're on. Its unit isn't kilograms, it's the Newton, named after Sir Isaac Newton, of course. And here's the total opposite of mass. Weight is absolutely not constant. It all depends on where you are.
And this force is with us all the time. It's what's keeping you in your seat right now. It's what makes a ball fall back down when you throw it up. And it acts like an invisible tether, holding satellites in their orbits around the Earth so they don't just fly off into space. It is a powerful, constant presence in our lives.
So we've got mass, the stuff, and we've got weight, the pull on that stuff. So how do they relate? Well, it all comes down to one of the most beautiful and simple equations in all of physics.
Weight equals mass times gravitational field strength. W equals mg. This simple little formula is the bridge that connects the two ideas. Your weight is just your mass, multiplied by the strength of gravity wherever you happen to be. It's that simple.
And for all of you studying this formula triangle is going to be your best friend. Seriously, just cover up the letter you want to find with your thumb, and the triangle tells you exactly what to do with the other two. Want to find mass? Easy. It's just weight divided by g. Super useful.
So what is this G thing anyway? That's the gravitational field strength. Think of it like a rating for how strong gravity's pull is at a certain place. Here on the surface of Earth, that value is about 9.8 newtons for every single kilogram of mass.
Okay, enough with the theory. Let's make this super clear. The absolute best way to feel the difference is to take a quick trip off-world. Let's go to the moon. This comparison says it all. Check it out. On Earth, a person with 70 kilograms of mass weighs around 687 newtons. Now, let's magically transport that exact same person to the moon. Look, their mass is still 70 kilograms. They haven't changed. But because the moon's gravity is so much weaker, their weight just plummets to 114 newtons. That means they'd feel about 6 times lighter, even though they are still the exact same person.
And this isn't just an Earth-Moon thing. It applies everywhere in the solar system. You know, if you could travel to Jupiter, you'd suddenly feel more than twice as heavy as you do on Earth. Then, if you flew over to Mars, you'd feel less than half as heavy. All that time, you never changed, but your weight was all over the place.
So let's just put it all together in a nice, simple table. Mass, it's the amount of matter measured in kilograms, it's a scalar, and it's always constant. Weight, it's the force of gravity, measured in newtons, it's a vector, and it changes depending on your location. This is a perfect little summary of everything you need to remember.
Okay, so knowing the difference is one thing, but how do we actually measure these two different things in the real world? Because, as you can probably guess, the tools are fundamentally different.
To find an object's mass, we need to use a balance. A traditional balance works by comparing an unknown mass on one side to a set of known masses on the other. Because gravity is pulling down on both sides equally, it just cancels itself out. That gives you a true measure of mass, a reading that would be exactly the same on Earth as it would be on the Moon.
But to measure weight, you need a force meter, which is also called a Newton meter. This thing is basically just a really well-calibrated spring. It directly measures the force of gravity pulling down on an object. And this reading would absolutely change if you took it to another planet.
Now, most of us in a lab or a kitchen today are going to use a modern digital balance, and they give a reading in grams or kilograms. So how do we use them the right way to find just the mass of a substance, like a powder or a liquid?
The key is what's called the zero or tear method. It's a super simple four-step process. First, you put your empty container on the scale. Second, you press that zero or tear button. This tells the balance to completely ignore the container's mass. Third, you add your substance. And finally, the number that pops up on the screen is the mass of your substance and nothing else.
And you can see that whole process right here. By zeroing out the balance with the empty container on it, we're making sure that the final number is only the mass of the stuff we actually want to measure. It's a really simple but totally essential technique for getting accurate measurements.
So let's just wrap this all up with one final simple thought. You can think of it like this. Mass is the amount of stuff you are made of. Weight is the force that the universe exerts on all of that stuff. One is what you are. The other is the relationship you have with everything around you.
And that brings us to a final, kind of fun question. If your mass is the one thing about you that's constant across the entire cosmos, but your weight is what connects you to every planet, every star, which one do you think truly defines you? Something to chew on. Thanks for joining me.